Good morning, everybody. Today, we're going to start the last chapter we're going to cover for this course, chapter 8. It's got 3 sections, and what it deals with is the entire concept of hypothesis testing, which is the whole purpose for really studying statistics, is to test a hypothesis or an idea that you may have based on your observations. All right, so let's define hypothesis. These are important. It's a claim or a statement of an observation based on some sort of observation about an existing property of a population. So this is very all-encompassing. A claim or statement. A claim is the different concepts here. A claim is you're asserting what you think just happened. A statement is you're stating what you just noticed. It's based on some sort of observation. It doesn't have to be by eyes. It could be by hearing. It could be by feeling. It could be by smelling. But that's what I'm saying. It's when we use the word observation about an existing property of a population. This population doesn't have to be of people. It could be of anything from microcellular to galactic in size. So we look at the existing property of a population. So we notice that in wintertime, the whales along the Pacific coast go north to the colder waters, because on the north hemisphere it's cold and the southern hemisphere is hot. So when it turns to be summertime in Alaska, say, all the whales migrate south to the colder waters of the South Pacific. So that's we're noticing that the property is the migration of whales based on temperature. All right. So we have a couple of ways that these things can be done. Here's some examples of them. We deal with portions, population, deviations, population variances. These are what we call our statistics, the mean, median, the mean, variance, and deviation. That's what we call our statistical inferences, our statistics, or the test of what we're going to look at. So a proportion would look like it could be equal to a half. Remember, this is our claim. Proportions deal with P, and so we're saying that we notice that happens 50% of the time. The deviation, that's our rho. We can say that that's less than 72. We're saying that this test was so difficult, the average of all my classes put together was less than 72. And the population variance, we could look at the population variance, that's population mean. Population variance is bigger than that. We'll also look at the population mean. These are our statistics. So those are some examples. And this is, we're going to have to do the hardest part about this subject or this topic is to figure out what is being stated. For example, let's look at example 1. Most internet users favor two-factor authentication. Whenever you log on, so you have to have your password and then some other code or something like that. So that's what this was about. It's the chapter problem that I didn't read out to you because I can't find it actually. It claims that it's claiming that most internet users favor a two-factor authentication. So we'll get the proportion here. So the proportion of people, what defines most? It's a very ambiguous term. All we can think about is we have 50% here. Anything bigger than 50% is most. Least. Or lesser. So we're looking here is, for our example, we're looking at our proportion, anything bigger than 50%. That would constitute the most. Simple majority. So that would be our statement. The proportion is bigger than half. In this example, our N was 926 users. We also talked about many times about significance. Is it significantly high? Significantly low? Or neither? High.
Or
yes. Yes.
no, it says neither high or low.
Yeah, that's when you say neither, because it's either significantly high, significantly low, or neither significantly high or low. We're looking at these two. So what would you consider significantly high? Remember, our N was 926. So what if we had half of that would be 463. So that's half. What if we had 460 people said that it was a good idea?
So that would be significantly low.
Is that really significant though?
because it's less than 50%.
It's, no, but that's, remember we talked about earlier, when we talked about significance,
Yes.
we have easily neither. This is significantly low. This is significantly high. So it gradiates from there. So there's a point somewhere where instead of significantly, we say it's clearly low, or it's clearly high. It's not significant, but we notice that it's, so if that's just the clearly, then there's some gradation here. This is only 3 less than half. Is that significant? Not really, because you still have 460 more to go through. So if anything, I would say that this one would be, it'd be low, yes, but not significantly low. Just because it's below 50%, it tells us that it's lower than average, but it's not significantly low. All right, so that's, again, this is why statistics is really more of a, it's not an exact science, because it's how you see it. We try to put numbers to them, calculation formulas, but if you come up with 460 people, you can't really say, well, that's a significantly low number of people. No, a significantly low would be like 200. That's very far below half. So that's what we have to be very, 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 very careful about.
So in this case now, do we say it's neither low or high?
Neither low nor high is right here in the middle. But since it's below the half, we know it's low. We say that this one is low, but in the very, we could say it's, in this one, I would say it's
Somewhat
somewhat
low.
low. Because if you say neither high or low, then you're looking at, yeah,
Okay.
it's very close to it. So that's why if you said neither high or low or somewhat low, yeah, I mean, that is talking about the same thing.
Okay.
So yeah, now you see why statistics is a very, very difficult. Really, that's the difficult part, is the human intervention part of it. Okay, let's see here. So let's look at the procedures. For hypothesis testing. So the whole process really goes like this: is you make an observation, you create a test, collect data. So the first thing you have to do is identify the claim. What is being claimed? From there, represent the claim symbolically. This is where you use the less than, equal to symbols. Once you do that, once you represent whatever your claim is, now comes the separation of the part pieces. Identify the null and alternative alternative hypotheses. No, what does no mean? Null means nothing. So the null hypothesis, which we represent with H sub 0, because remember, what you observe is compared to what's happening naturally. So the null hypothesis will pretty much relate to if nothing changes after you do your test. This one contains the equal sign. It could be less than equal to, greater than equal to, or equal to. So this is what we call homeostasis. That's what's happening right now in the real world. The alternative we represent that one with H sub 1. This one does not contain
Equal to.
the equal sign. So it's going to be less than, greater than, or not equal to. Because this is what you're saying. You're saying, because it's again in a card game, the null hypothesis. If we're playing a game called War, where whoever has a higher card, the dealer, if the dealer has a higher card, then they win. If the cards are the same, the dealer wins. So the only way that you can win is if your card's higher than the dealer. So your cards will have to be higher, strictly higher, not equal to. So this first part, these first three sections, that just sets up your hypotheses. Now the fourth step, choose a level of significance. And what we've talked about that is your alpha. So you can say like, I want my alpha to be 0.05 or 5%. Which means here's the mean. Let's say that we wanted something higher, the game of chance. What this thing says is your chance of winning is 0.05. Your chance of losing is 0.95, or the 95% confidence interval. So anywhere from 0 to this number, you lose. That's the confidence interval. The reason I use 0.05 is because that's usually, whenever you read articles, that's usually the safest one to use. Remember, if you wanted to, you can use 0.99, 0.01, 0.10. This is 95%. This is 99%. This one's 90%. So again, it's up to you to choose which one you want. All right, now from there, so you've made your claim, you determine the hypotheses, the alternative hypothesis, you've determined the level of significance. Now you got to what test statistic you'll use. There are three primary types. Proportions. That's when we use the p-value. We call it the p-value method or model. We have critical values, which is called the critical value method. Remember what critical values were? The critical value is when we found this value here. Like we said, for example, we said +2, the mean +2 standard deviations. So anything to the right of it is what we're looking for. Anything below it is not. So this at this value here, that's the make or break point, which is called the critical value. And then the last one is chi-squared, which is like that. And if we have time, I'll show you how to do that one. So now, once we decide which one of these methods we're going to use, now we got to find the values. Once you find the values, you have your test, you have your critical values now. Now you test whether you make your decision, is it going to pass or is it going to fail? So in other words, when I say test, I'm saying the values you're going to use on your experiment. These are the statistics that we talked about earlier. So you have your critical values, you have your hypothesis, you have your confidence level, you found use your test values. Now you make a decision. Do you keep the null hypothesis or reject the null hypothesis? Okay, again, and that's all depending on where your critical values. If your test says I'm looking for things higher than this, then if it's lower than it or equal to it, I keep the null hypothesis and I reject my hypothesis. I'm saying that's going to happen over here. If it happens below there or equal to it, I lose. So this is my H1, this is my H0. And then last step, I don't have room to put in here, is conclusion. In words, tell me what happened. Remember, these are the the significance levels. Remember, the most common ones we use are at 90%, which is 0.10. Or we have 0.05 or 0.01. That's what we use, for example, the t-test, the chart for the t-test. We had to determine whether it was one tail or two tail. And one tail, it could be one tail left, one tail right, or two tail. And this is what we're looking at. So if it's 0.10 for a two-tail test, that's the most common we use. That's the 90% we're looking at. Sorry, one tail is 80%. Why? Here's the first question I have for you. Why is it 90 for two tail and 80 for one tail? Because 0.10 represents the amount of area in that place.
So for the two sides, for two tail, we're going to have 5% each on each left and right.
Yes.
Tail.
No. Yes. So the total is 10%, which
And
is
the
two.
middle will be 90%.
Right. Now, for the one tail tests,
so each of the tail is going to be 20%, while the middle will be 80%.
because now what we're saying here is you want to be 10% confident. This is the most typical one, two-tail test. So if it's two tails, if we had it two tails, we using 10%, that would be 10 and 10%. But since we're pushing everything over to the one side, what we're looking for here is 80%. Because this one's always going to be double this one. Remember, we do the alpha over 2. So to go from that value to here, we double it. So as for this one, what would that one be? Well, this one would be 95.
95.
So that's 5%. Now for this one,
90%.
90%, which is twice as much. For 1%, this would be
99%.
And this one would be so times 2 makes it 98%.
98%.
So that's what we're looking at. That's now the rest. This is just standard now. And if we wanted to, we can go through and see what the z-scores and the t-scores are. Well, we can't do the t-score because the difference between, remember the z-score and t-score charts? The z-score chart had 0.0 on down here, and this one here was 0.00. So it didn't matter how many elements we had. We just looked at whatever our formula gave us. Whatever our formula gave us, we'd have it in 2 decimal places, and then that'll give us an area. The t-score chart, on the other hand, It's made up of the degrees of freedom here on this column. And up here, it tells us whether it's a one-tail or a two-tail test. And then it goes from 0, 1, 0, 5, and so on and so forth. What is degree of freedom? Remember the formula for degree of freedom? N minus 1. Because it's important. When we use the Z versus the T, we use the Z table if we know the population, either variance or deviation, or the mean. If we know anything about the population, we use this one. But for T-score, and your standard deviation of the population is not known, and your N is less, I know it's greater than 30. But yeah, we did those yesterday. All right, this is a good example. Now, one through.
Mister, you said the T-score. Can you explain the T-score again?
When will you use a T-score? Basically, use a T-score chart if you don't know anything about the population.
Okay.
Because remember, the whole purpose of these experiments is we want to go from the sample mean, we want to be able to predict the population mean.
Okay.
So if we know anything about the population, we use a Z-score, then it's our numbers. But if we don't know anything about the population, we can have a large data set, but again, it's still maybe insignificant. If we had 3,000 people and we're trying to look at the entire nation, that's very insignificant. So that's why we use a T-score chart and try to break it up even further from there. This N-1 takes in consideration how accurate your sample is going to be. That's why we subtract 1, that removes any bias or outliers. And then but again, we don't know anything about the population.
Okay, thank you.
So again, the null hypothesis, it's also called the working assumption. Because remember, what you observe, okay, when you're with kids in wintertime, and they say, why are the leaves are changing color from green to brown? Okay, so what does the kid originally think that leaves are? Thinks that the leaves are green. So therefore, anything that's not green is not normal to them. So something's happening. So this is your null hypothesis because that's what's happening. And this is your alternate hypothesis. It's changing. You're trying to find change. So our null hypothesis is, well, our first example, we had the internet with proportion being 0.5. That's the null hypothesis. The alternate hypothesis which is H1. How are ways we can counteract that? If we're saying P equals 0.5, then the opposite of that would be P does not equal 0.5. Or we can say that since it's not equal 0.5, there are two possibilities. It can be less than 0.5, or it could be greater than 0.5. So the hypothesis we're saying is if it equals 0.5, we would take any of these to counteract that one. Because if it's less than 0.5, it's not equal to it. If it's greater than, it's not equal to it. If it's not equal, it's not equal. So again, the alternate hypothesis, depending on what you're looking for, is how you state it.
So the alternate hypothesis does not have equal to. So that's why we don't have less than or equal to.
Correct.
Okay.
The alternate hypothesis does not have an equal sign. I'm trying to find an example. Because there's significant levels with hypothesis testing. Again, what is our significance level? Is our alpha.
Alpha equals to 0.05.
So what does this really do? It tells us, okay, since we're using alphas, our confidence level is 0.05. That means we're looking at 95%. That's 95% of the data that could ruin our observation, our hypothesis. So what we're looking for is, now, if this is true, if our data does fall in here, here's the alpha. So if our data falls over here, is this our H1 or HO?
If it falls,
Well, no, but if it's, because we always are, what we're looking for is always the tails. Everything here, less than or greater than that, that would be our HO. So if this is true, that means if our null hypothesis is true, what does that mean?
it means it's greater than or equal to, or less than or equal to.
So if we're saying, yeah, it's if our answer is here, that means our our alternate hypothesis fails. And this is what we're going to work on this chapter. This is the tough part, because what we have to, when we state our hypothesis and we state our critical value and choose our significance level, Each one of those play a particular part that tells us that has to be in place in order for it to work or not. Table 8.2 in your chart, in the sheets I gave you. Let's look at these parameters that we're going to be using. Those are the tests. Sampling distributions. The requirement. And our test statistic. The test statistics, again, that's the formula. That's the how we're going to find the numerical value for it. So the first one, we're going to look at proportions. That's our letter P. What we're looking for here is called a p-value. Sampling distribution. In order to use the proportion, we have to make sure normally distributed. We use the z-score. So what are the requirements for this? Since we're using proportion, with proportion, we have P is for success, and Q is failure, or not success. So the requirements are that the probability of success has to equal the probability of failure. Or not, it doesn't have to, but there has to be a correlation. It has to be at least bigger than some n. And our z-score formula is our proportion of the sample minus proportion of the population over P times Q over N, square root of it. That's what we did earlier last chapter. If we have the population mean, which is the mu, if we use the t distribution, what are the conditions here? There's two of them. The deviation of the population is not known. Oop. It's not known, and it has to be normally distributed. And normally distributed. Or if that's not what you have, then again, we don't know the population. And n is greater than 30. So we have a large data set. But in both cases, we know nothing about the population. So it's either normally distributed or the sample size is large if we don't know the standard deviation, the population deviation. It's the t-test, so we use a t-score, which is x bar minus mu s over n. Why do we use s? Why do we use x bar? Because the population deviation is not known, we have to use s. And since we don't know the population, we have to use a sample, and those we put our sample size in there.
Okay.
The population mean again. Mu. normally distributed. So we use the z-score. That's the sampling, normally distributed. The difference between the z and t is in the z, the population deviation is known and normally distributed, or the population deviation is known and n is greater than 30. So if that's the case, then we use our z-score. X bar minus the mu.
Oh, okay.
So,
Got it.
yeah, and you notice how they're almost identical? It's just that the z-score is more accurate because we have the population deviation as opposed to the sample, which is t.
So, Professor, so if you don't know the population deviation, we use t-square.
You have to use t, right?
Yeah, but if we know it, we use c-score.
Yes.
Okay.
Because once you know the population, then that number came from a larger sample size than you really had. So that much is known already. So yeah, that's why the formulas themselves is not the problem. What the problem is once you get these values, you have to go to the chart, and the values are going to be just a little bit different there because of the accuracy of where the sample came from. So even though you may get the same numbers, the information on the charts were different. And the last one is the standard deviation of the population, or the variance. We're not going to do chi-squares yet. Remember the difference between these two. This is deviation. This is variance. So the standard deviation is the square root of the standard variance. Typical, when we look at this, we're looking at the chi-square. The formula is pretty straightforward. For this one, it must be normally distributed. And of the population. Because this is very, very, very strict. It has to be normally distributed and it has to be of the population. So the chi-square, you notice it's not just an X, it's a squiggly X. It's the Greek chi. So here we have n-1 for accuracy. Since we have the population, we have the this is of our sample. That was, yeah, because deviation of the population is more exact. So we have the sample variance over the variance of our population. Now, okay, what's important here is the reason this is stated here in the first column is you can be given in a question, you could say that the population deviation is 3. Do you use the population deviation in your formula? Well, you kind of do. It's right there. All you have to do is square it. Even though the formula asks for the variance, If it gives you a deviation, just square it and there you have it. I don't have many examples here. When we talk about test statistic, and notice in our steps, the test statistics are used to test our null hypothesis. For proportions, remember we used P and Q. That's with the hat. This is of the sample. And so the sample, we use the deviation or the variance, which is S squared. So once we get these, we find the Z, T, or chi-square, whatever we're being asked for. And then from there, we form our conclusion about the null hypothesis. Because everything is in reference to the null hypothesis. Why is it null hypothesis? Is because that's the only thing that's constant. It's true. Your null hypothesis could be false. So we're only comparing it with respect to the null hypothesis. Here's an example. From example 1, we have a claim made about the population proportion P. How do we know that that's going to be population proportion? It doesn't have a hat. If it has a hat, then it means it's of the sample. Okay. From our example 1, our N was 926. Our P hat was 0.52. The null hypothesis was that it's looking at most of the people surveyed believe that you needed two factor identification. So what we're looking for is 0.5. Half of the people, because if it's exactly half, then it's not going to work. Or if it's less, it's not going to work. So we're going to look at that value first. So once we find the P, how do we find the Q? P is equal, well, let's see. P plus Q has to equal 1. Success plus failure equals 100%. Since we have P, to find Q, I just subtract 1 minus P. So if P is 0.05, then Q is 1 minus 0.05. Q is also 0.5. Here we have N. Is this a one-tail or a two-tail test? Or does it matter? Doesn't matter because we have the population information. So we'll use the z-score. Our formula for z was p hat minus p times q over n. Our p hat was 0.52 minus our population proportion is 0.5. P was 0.5. Q we calculated also 0.5 over N. N was 926. Put that in our calculator, run it through, we get 1.22. So we could look at this, pretty much helps us define our critical value. Because that's going to be out, that is going to be our critical value, because if we're using the mean, we're looking here is, it is 1.22 to the right. Anything higher than that is for our alternate hypothesis, H1. Anything below there is H sub 0. All right.
Excuse me, Professor. Please, the last sheet, is it 0.52 or 0.5 square?
This one?
Yes,
Or
the
what?
one on top. Yes.
It's stated, it's the p hat is 0.52.
Okay.
And that was stated from the question. From the chapter problem.
Okay.
So the next step whether it's one tail or two tail. If it's one tail, is it one tail left or one tail right? And what number corresponds to this line here? What's that called?
The critical value?
That's the critical value of CVs. Now, since that's the critical value, what this part here, what that defines is called our critical region. Region. It's the area that make us reject our HO. If it falls here, it can't fall there, so we reject the HO.
If it falls on the right?
If it falls in the tail,
Yeah.
If it's a one tail left, one tail right, if it falls inside the tail, then we reject the HO.
Okay.
So let's get one tail left test. For a one tail left test, what do we have? The critical region
Region.
is on the left side. Or left end, I should say, of the curve. When I talk about the curve, I'm talking about the bell curve. If it's a one tail right, that test will tell us the critical region is on the right-hand side. The critical region is on the right end of the curve. So what do you think about two-tail? The critical region is at both ends of the curve. Oops. It's there and there. Oh, yeah. As you said earlier about the statements for the null and alternate hypothesis. So what symbols can be used with the null hypothesis?
Less than. Greater than. And no equal to with a slash.
You just define these because the null hypothesis has to be the equal side.
Oh, sorry.
The alternate hypothesis are these.
Oh, okay.
Because remember, it has to be strictly greater than, strictly less than, or strictly not equal to. And what's the shaded region called here?
Critical region.
That's the critical region. So once we define our critical values, if it's a two test, if it's to the left of the lower bound or to the right of the upper bound, then the null hypothesis is rejected and the alternate hypothesis is true. All right, let's look at an example with numbers.
So which one is true out of the two?
It all depends on what the statement is. If the test value you're doing, if your test statistic gives me a number that falls in the critical region, then that means the null hypothesis is rejected and we can accept your alternate hypothesis. I put that in quotes because more tests are needed. It's just that we can, with what we know so far, we can use that alternate hypothesis. So, and here's an example. Our N, we're using 926. This is the example, the chapter example of people who think that we should need multiple factors of authentication for computers. The N is 926. The P hat is 0.52. What this thing says is that 52% of the people think that we should use multiple factors of authentication. That's what that says. And we used an alpha of 0.05. Now, what is the Z? Do we use a Z or T score here? We use a Z score because if you think about it, I mean, half of the world thinks we should, half the world thinks we shouldn't use multiple factors of authentication. It's a great idea. It just takes lots of time to do it. I'd much rather just turn my computer on and start working. So because of this, we use the Z score. Remember the formula for the Z score? Of proportions?
Spear over S over square root of cap P cap Q over N.
So calculate these. We have 0.52 minus 0.50. The P,
0.52.
well, this is the population. This is 0.5 times 0.5. It's the population on the bottom over 926. So what does that equal? To my calculator. So on top we have 0.5, no, just on top is going to be 0.02. Top we have 0.5 times 0.5. Divided by, that's 0.25. Divided by 926. Is 0.02. And then I take the square root of that. Zero 0.016431019 497. So now it's dang, I gotta retype this one. Try this. Yeah. We get 1.2172, which since it rounded 2 decimal places is 1.22. So my z value is 1.22. That's my critical value. What do I do with that number? I go to my charts. And I go to my charts. Since I'm using the z-score, I can use the z-score chart. So it's 1.22. So the 0.2 is the third column. 1, 2, 3.
That's 0.8888. Positive z-score. 1.2. What's the answer? I think it's 1.22.
Yes.
0.8888.
Yeah, with our information then, so it equals 0.888. So what do we do with that?
That's 88.8%.
Yes, so that is this area here. So this area here is 0.1112. And this part here is 0.8888. So that's our p-value. Okay, hold it now. Five to that, 5, 5. PQ. Let me try something real quick. So we have 0.52 times 0.48 divided by 926. Square root that. reciprocate it times 0.02. And I get 1.22 again. All right, good. So that is our p-value. That's the determination. So the question I have in this one is, why did we use proportion in the first place? Why did we use proportions in the first place? Because what does a proportion tell us? Proportion, P, is like a simple average. Say we had 426 over 926. That gives us the decimal value. That is our proportion. What we're looking at here is, since we're saying that we have a 52% of 52% of the people favored using these two-factor authentication. So it's 52% of the 926, which is 0.52 times 926. That equals our 482 people. So this is what our P would be. The people who, so the 482, that's our, I mean, up here, our sample size. Because these are the people who wanted it. So the proportion of the 52% of the people who favored multiple factor authentication constitutes 482 people. That means the people who didn't want it constituted 0.48 or 48% of the people, which was 926 minus 482. $444 people who didn't want it. So if we could break it down that way, then we could use the proportion method as opposed to the critical value method, which is where we would use our X bar type stuff. Critical value method. Traditional. This is what is mostly used for hypothesis testing. All right. So, and this is what we normally use. Let me see so in this one. So we see here, here's our critical value. The critical region is this part bigger than that. Our midpoint is 0.5. That's also where the mean value is. The Z value is 0. It's the mean. Since the half people to the left, half people to the right. What we have to use now is we're going to use these separate values. We're going to use our hat is 0.52 because we're looking at 52% of the people favor it. So if 52% of the people favor it, then that corresponds to a Z value of 1.25. With our confidence level at 0.05, the critical region is anything to the right of that. So if this critical value here is 1.25, if the Z value of our sample falls to the right of it, like this one does, then we keep H1, reject HO. But this is in quotes, really. And this was saying, this is where it's important. This is the mean. This is where our P is 0.5 and it equals 0. And this is our critical value at 1.25. If in our test, this is our critical region, so if our value falls in the critical region, this is our H1, this is our HO. If our p-value is above our critical value number, in other words, if it falls over here, fail to reject HO. I mean, I'm right here. So if this is greater than our alpha, remember our alpha was 0.05. If it's greater than alpha, it's on this side. So we fail to reject HO. If our p-value is less than or equal to alpha, then we reject HO. So the whole purpose is we have to now find our p-value. In English now, if the test statistic, whatever we get from our calculation, is in the critical region, reject HO. If the test statistic value is not in the critical region, then you fail to reject HO. Because it's all relative to our null hypothesis. All this really tells us is we have more testing to do. So here's an example. Our test statistic gives us a value of Z equals 1.25. The critical region is to the right of Z equals 1.645. What do we do? If our test statistic gave us this, and our critical region is to the right of that, what do we do? Our critical region is anything bigger than 1.645. This is my critical region. My test statistics gave me a value at 1.25. It's not in the tail. So what do we do?
You reject it.
We reject it if it's in the critical region. Since it's not in the critical region, we fail to reject HO. So again, it's the wording that gets a lot of people confused. So
What does fail to reject mean?
you can't reject it.
Oh,
Your null hypothesis, it hasn't changed. So you really can't do anything with it. So all you know is your test wasn't good enough. You can't really use except, you can't use the word except in the null hypothesis because there's too many other things we could have done the test wrong. We could have done the calculation wrong. So instead of saying accept this hypothesis, we would do is says well, all we know so far is failed to reject the null hypothesis because it falls in the HO region. If it falls in the H1 region, then we can reject HO. Make more sense now?
yes, sir.
Confidence intervals for hypothesis tests. Confidence interval. So the word confidence in there. How do we calculate the confidence interval? How do you find the confidence interval? One way we talked about this was this way. Where you add and subtract the margin of error from the mean. And so this defines our confidence interval. But where do we get this stuff from? Where do we get the E from? What do we need to do? Anybody? How do we find the plus or minus the error?
Error is mean
or we'll use the Z times N times P. Yeah, in many ways, it all depends on what we're given. So that's how we find confidence. What does the confidence interval consist of? What's between these two numbers? What's between these two numbers? What does that mean to us?
Less than mean.
So if I said this, and I'm doing a 95% confidence interval, what does all this stuff mean? What it tells us is, in a nutshell, is that there's a 95% probability that the population mean will be between these two values.
Okay.
So that's what it tells us. On the bottom, equivalent methods. Are they all the same? Using different parameters. Here's our parameters. We have proportions. We have the mean value. This is P, this is mu, and we have the deviation, which is the rho. So what this is saying now is the confidence interval equivalent to a hypothesis test that leads to the same value. So is the confidence interval equal to or equivalent to a hypothesis test that leads to the same value or conclusion, I should say, instead of value? Can't use value because that means the numbers are the same. So are they the same? We just talked about confidence interval up there. The hypothesis tests is not an interval, it's a specific value. But if no matter what method we use, if they give us the same conclusion, are they the same? For proportions, it's no. And for the mean and deviation, it's yes. Why? Because the mean and deviation build off each other. You find the deviation by knowing the mean. So if one of them is right, the other one's, and that's going to give us the same values. But a proportion depends on the critical value and the sample size. So that's why it's no, because both of those can change. So in other words, do not if you're looking to test a hypothesis, don't use the confidence interval method for proportions. It's more accurate using the specific hypothesis test for proportions than confidence interval testing. That's just to keep you from making errors. Type 1 or type 2 errors. Well, let's look at, we're looking at here is when we're looking at hypothesis testing, our entire purpose is to compare our sample average, our mean, to the test mean. So we're looking here is sometimes when we do this, our calculations, our solutions are going to be wrong. What can we do to fix that? A type 1 error occurs when we mistakenly reject the null hypothesis when it is actually true. Actually true. So a type 1 error is when we reject the null hypothesis when it is actually true. In other words, what that means. If our test value falls inside this bigger part and we reject it, even though we should keep it, we reject it anyway. That's a type 1 error. And alphas are usually used to represent that too. So the probability of a type 1 error. Type 1 error is the probability of rejecting HO when HO is true. That's a type 1 error. You'd be surprised, it happens a lot of times. A type 2 error is just the opposite. Occurs when
Just false.
we mistakenly I can't say keep. I was gonna say keep. Fail to reject HO when it is actually false. In other words, if our value falls inside the critical region and we fail to reject it. So these are just the opposite. You reject it when you shouldn't have, and you keep it when you don't reject it when you should have rejected it. So a type 2 error is written by the letter beta.
better. Okay.
It's the probability of a type 2 error. Failing to reject HO when HO is false. And should be rejected. It's a lot of stuff to memorize. Yeah, there is a mnemonic for it. It's reject, true, no, hypothesis, reject, true, no, and this one is fail. Term reject, true, no, and fail to reject
False.
a false no. So it's FRFN. It the word is routine for fun. Reject. RUTN, routine, the consonants. For fun. So it's routine for fun. Or you just think about it as just the opposite. If it's supposed to be failed and you don't, and it's supposed to be kept and you don't, just look at it that way. Just look at two possibilities. And the last, this is last example. No, we have one more after this. Yeah. Example 2. Type 1 and 2 errors. Okay. Consider the claim that, here's the claim. A medical procedure designed to increase the likelihood
Of having a baby girl.
of a baby girl is effective. So that the probability of a baby girl is what is that probability?
P. 0.5.
0.5. But that's not really a medical procedure. That's not really a medical procedure because it is exactly 0.5. Oh, well, we'll just go from here. Given the following null and alternate hypotheses, write a statement describing the type 1 and type 2 errors. So given H sub 0 is P equals 0.5 and H1 is P is greater than 0.5. So it said here we're supposed to write statement describing type 1 and type 2 errors. Type 1 and a type 2. So remember what a type 1 was. Type 1 error is what?
Mistake of rejecting a true null hypothesis
When it should be rejected.
when it
Right.
should be rejected.
So how would we write this? We have to write a statement for it. Because remember, this one, it is reject HO when true. So how would you state this? Remember, you're looking for a medical procedure designed to increase the likelihood of a baby girl is effective. So what's the null hypothesis of this one? The alternate hypothesis is this procedure
Increase.
will increase the likelihood of a baby girl.
Mhm.
That's H1. So HO is, there is no effect. No, you can't increase the likelihood. So here, they're saying here that the procedure is effective despite not being accurate. We should have rejected it because it doesn't do anything,
Mhm.
but we kept it. Type 2 error.
That's the mistake of failing to reject the null hypothesis when it is false.
Fail to reject HO when false. So failing to reject it when false. What will we do here then? Failing to reject it. What is the likelihood of occurring?
Greater than 0.5.
Or HO, or null hypothesis says you can't reject, you can't predict.
Okay. So P would be 0.5.
So we're saying here, yeah, but the P being equals 0.5, and it really doesn't mean anything to us yet. Is because we're saying here is the likelihood of a baby girl is 50%, no matter how we look at it.
Mhm.
Even though the medical procedure is saying that we can increase it. So it should be false. But we're not going to reject it. We fail to reject HO, even though we know the statement's false. Even when HO is false. So the procedure, the effectiveness of the procedure is false even though the procedure does increase the chances. So you're failing to reject HO, even though we know it's false. So the effectiveness of the procedure is false, even though the procedure can do it. How do you distinguish between type 1 and type 2?
Yeah, they better enough.
Okay. Yeah. And the type 2 errors are used to describe the power of a hypothesis. Oops.
Oh.
The type 2 errors are used to determine, not describe, determine. So by power, of a hypothesis, saying it's the probability that 1 minus beta, probability of 1 minus beta chance of rejecting a false HO. So the power is the probability of 1 minus beta. So it's a type 2 error. 1 minus type possibility of type 2 error. Let's look at that. Example. Even though, I hate to say it, even though the power aspect is not really used that often anymore, we have to discuss it anyway. Okay, this one. Power of a hypothesis test. To consider these primary preliminary results from the XSort method of gender selection. There are 13 girls. From 14 babies. Born to couples using XSort method. If you want to test that the claim that the girls are more likely or that means greater than 50%. With XSort. We get this. The null hypothesis is what? The null hypothesis is what currently stands out there. What is the current state chances of baby being born a girl?
50%.
So P equals 0.50. Now, the alternate hypothesis says what is being claimed? They're saying that they could increase the number of girls. So that means that theirs is going to be bigger than 0.5. Using alpha equals 0.05. Find the power of this hypothesis. All right, here are your steps. We have enough, yeah. We have to do, since our P is 0.05, what we have to do is we have to look at values in this case, since we're looking for this. We got to look at what happens at P equals 0.6, P equals 0.7, and so on and so forth. We look at higher, since our alternative hypothesis said it's increasing it. So we have to look at what happens when it gets higher. Because it's going away from the norm. So what do we do here? Here's our test values. of P. So we have 0.6, 0.7, 0.8, 0.9. And we look at the power of the test, which is the formula 1 minus beta. So what do you think the beta values represent?
I think it represents the percentage of likelihood of having baby girl.
Well, yeah, because now since we have in our event, one of two things can happen. The baby come out boy or girl. So we have a binomial distribution. So the beta aspect is the probability of that occurring. And crikey, since running out of time, we'll just use the values that are given. But there's another table that deals with binomial probabilities. We just look at what is our initial probability and calculate the beta. 0.820, 0.564. And what do we notice about our values?
Our value increased, but as the probability was going up, is decreasing.
Decreasing, right. So it's 1 minus 0.820 makes it 0.180. 1 minus 0.564 equals 0.436. 1 minus 0.227 is 0.773. 1 minus 0.012, 0.988. So what does that tell us? What this tells us here, the power of the test at 0.06, 0.180, this is 18%. Not too good of a chance. 43.6%, 77.3%, 98.8%. Getting even worse. So this is the probability of a type 2 error. So the larger our p values of success, the larger our chance of making a mistake. Yeah, again, this type of analysis, again, it's very rarely used. So what we would do there is this would be some of the extra information presented at the end of a analysis if you use one of the software. And the last one is not really much of an example. It's just a walkthrough. Finding the sample size required to achieve 80% power. Here's a statement from an AMA journal. The trial design assumption that with a 0.05 significance level, 153 randomly selected subjects would be needed to achieve 80% power to detect a reduction in the coronary heart disease from 0.5 to 0.4. From that statement, we could do the following. Before conducting the experiment, the researchers selected a significant level of 0.05 and a power of, they decided that themselves on their test design. The researchers decided that a reduction from the proportion of coronary heart disease from 0.5 to 0.4 is an important difference that they need to watch and detect. Again, who decided that's an important value? They did. There's no proof of why they chose it from 0.5 to 0.4. What is the significant difference there? Using a significant level of 0.05, the power of 0.8, and alternate proportions of 0.4, technologies has Minitab used to find the minimum sample size is 153, which is what they decided. That's why they got that many. So this is what they're saying is, remember, so at the beginning of the semester was that the statistical tests that we do, we have a lot of choices. We select how of what we're going to do, how we're going to do it, even determining the sample size we need. That's just a number we pick, or is calculated from what we pick from up here. Why at least 80% as a power? Remember, what is a power? A power is 1 minus the type 2 errors. So what this says is if our type 2 error was 20%, then our power is going to be 80%. 20%, that's a lot of errors. That's 2 out of every 10 sample is an error. Why do they pick 20%? Because if they chose 10% for a power of 90, their test wouldn't work. So this is, once you do a test, once you do a study, you can now manipulate what these numbers are going to be. Instead of from 0.5, instead of going down to 0.2, which would have been more significant. Well, that didn't work. 0.3 didn't work. 0.35 didn't work. So they chose 0.4 because it would work there. Why 80%? Because 90% would be too tough. So a lot of this stuff, again, is chosen just to make sure your test is going to work. And when you have 100, this calculation says we want 153 subjects. Yeah, it says here, because there are certain things, the subjects may not show up. The subjects may not answer all of the questions or may not participate 100%. So you always, a good rule of thumb is a 10% rule. If it says get 153 people, then get 15 or 10% more of that. Get 16 more people. Try to get 169 people. Because chances are 10% of them aren't going to succeed and finish everything. All right, that's it for that section.